Okay, so we are doing stereo. Last time we talked about. Oh, okay. So last time we started talking about stereo, and we said that stereo means trying to estimate the depth from images. Of course, our images are two-dimensional images, regular intensity images. But this time we are going to estimate depth from images taken by more than one camera from different viewing angles. Just like the human eyes, humans have two eyes, and each eye provides one point of view of the real world. And all this data from the left eye and the right eye, they come to the eyes, and they are from the eyes. We immediately start processing the visual information. And at the back of our heads, there is this visual cortex. In that place, many vision-related processing occurs, layered processing occurs. And that's why we say that why don't we do the same thing with the cameras? I mean, place two cameras like this. They look at the same world, they look at the same scene, world scene, from two different angles. And by processing these two images at the same time, maybe we can estimate the depth. And we looked at this picture last time, as you remember. We said that, do you guys remember this term disparity? Disparity is this. If this is my left eye and this is my right eye, how the points differ from each other in terms of their position. As you see, this point here is away from the left edge of the image, but this point is not that much away from the left edge of the image. So this is maybe 50 columns. This is maybe 30 columns. So the difference between them is just 20. So that's the disparity for this point. So, but if we do the same calculation for these two points, we see that the disparity is not much, it is 5. So we observe that if the calculated disparity is large for a given point, the disparity, as you know, is extracted from these two images, then we say that that point is close to us, otherwise it is far away. Okay? So once you calculate this disparity, maybe you can build a disparity image like this, show it like an intensity image. So the brighter points are close to you, darker points are away from you, and that's called the disparity, and that's kind of a depth image. Okay? So basically in a stereo, from stereo we expect this kind of an image. Once you have the disparity image, okay, if you know your camera parameters, then it is easy to calculate the XYZ points of the real world objects by looking at this disparity, and we are going to show you how. Okay, so that's the basic of the stereo processing. First, we will have to extract this disparity image from these two images, left and right image. Then from the disparity images, we can calculate our absolute XYZ positions or the depth position. But most of the time, I don't need to know how far those objects are away from me, okay? All I need to know, maybe do the segmentation. For example, I know that this object is like this. I can nicely segment it. I can nicely separate it from the background objects. Or I can nicely separate this object from the background. That may not be that possible if you look at just the intensity of the images. Okay, so I mean, by looking at this, maybe I cannot tell exactly if this is a if this object is part of the background, part of this cloth, or is an object, okay? But if I look at this one, I see that, yeah, well, that's an object because its depth is different from the background, okay? So most of the time, the disparity image is enough for me. I don't need to calculate the absolute XYZ positions. Good. So we already know these, okay? We already know that given a point in the real world XYZ, I can calculate its projected point on my image plane by these two basic formulas. Okay, we did much more complicated calculations than this that involve the camera intrinsic and extrinsic parameters. So there is nothing new here. But just to make this picture a little bit less complicated, okay, if we take only the plane, just one of the planes of these three-dimensional world, okay, so I see this, okay, I am looking at just the XZ plane. In the XZ plane, I see the similarity of the triangles. So by looking at this triangle, this one is going to give me this equation. X is equal to F times X over Z. That's nice. And if I do the same thing with the YZ plane, I am going to get the second equation. Those are our basic equations, right? Those are our basic equations, and we know those. But last time, I think I stopped at this point. We said that those equations are nice, and they tell us something like this, okay? If I have a point at x, y, z, I know that its projection will be at this point. I know this. And these formulas give me the same thing. So x is equal to f times x over z, y is equal to f times y over z. I know this much, okay? But if I multiply x and z with the same number, I'm getting exactly the same xy, right? So that means what? Infinitely many points on this line will project to the same point, okay? Will project to the same point. So that means, well, this is expected because I am projecting 3D world to a 2D image, okay? And I have to lose something from 3-dimensional world to 2-dimensional world. I have to lose something, so I am losing the depth of all those points by doing this projection. Okay, that's what I am doing. That's why it is difficult to get depth information from a single image. I am not saying that it is impossible. It is difficult because, I mean, how can you get the depth information from a single image? By looking at a single pixel, you can't. But if you look at the neighboring images, neighboring pixels, maybe there are some ways of getting it, maybe some approximations and etc. Okay, so the point here is that if one image is not enough, let's look at the same scene from a different angle. Remember, yeah, I think last week, I think I stopped at this point. I drawn all these lines and everything. We said that. Let me erase all of them. Okay, we said that all of these points, this red point, green point, yellow point, they all project to the same point P here, but they project to different points on this image. On the left image, they are just a single point. On the right image, they are just many points, right? They are just many points. So what does that mean? It means this. If I know that this point P corresponds to this point P on this image, if I know that these two correspond to each other, then I can definitely draw this line and draw this line, and their intersection would give me the XYZ point of that P. So if somebody can find the corresponding point on the other image, then I can do this triangulation. The nice thing is this: how am I gonna find the corresponding point in the other image? Okay, I know that this point P, okay, has to be on this line, right? And if point P has to be on this line, the corresponding point on the right image has to be on this line. Okay, so I know that on the right image, on this line, I can make a search for P. Once I find it, I can infer the depth of point P. Okay, so I don't have to make the search in the whole image. I make the search on a single line only. Okay, that's called epipolar constraint. Okay, that's called the epipolar constraint. And epipolar constraint tells you that if you are looking for the corresponding point in the other image, then don't search the whole image. Just look at a single line. And where is that line? I'm going to give you some formulas. We are going to derive those formulas, and you will see that finding that line is not that difficult. And in fact, let's go back to our original image. It is not coincidence that, okay, it's not a coincidence that all the corresponding points on the left image and right image, they happen to be on the same line. Okay, it has to be on the same line, but I think I couldn't draw it. So let's look at this one. Okay, line, yeah. See this point here? Can you see it? Maybe you can. Okay, this point is on the same line here, this point. Okay, their columns shift, their columns change, but their lines are the same. Okay, and the same thing is here and there. These two, their lines are the same. Okay, and the same thing is here, so their lines are the same. What I'm saying is that when I make a search on the other image, I am looking at the same line. So this is not coincidence, because these images are adjusted, calibrated that way. But fundamentally, there is a rule that you are going to make a search on the same line. Okay? These images are on purpose rectified. Rectified images, they contain the corresponding lines, they contain the corresponding points on the same line, okay, of the other image. Okay, if this point is on the line number 100, then you are going to look at the line number 100 on the other image. The column, I don't know. I am looking for the column number. Okay, so the y positions are the same for these rectified images. Okay, not all images are the rectified images, but the rule is the same. You need to find a line and look for the corresponding point on that line. Okay, for the rectified images, all the corresponding lines are parallel and they are at the same line of both images. Okay, good. By the way, this constraint is called epipolar constraint, and we are going to come to that at the end of this lecture maybe. Okay, Y stereo vision, okay. The most familiar example is for us is our eyes. We should normally have two eyes, okay, and left and right eyes we see the world from different points, and people have realized this, and they did lots of experiments about it. They invented some toys about it, and we are kind of amazed about seeing the world from two different angles. We call this parallax. Parallax is your view change from left eye to right eye. Okay, if I do this, close one of my eyes and look at the world, and close the other eye and look at the world, I see two different worlds. Okay, and the difference between left and right eye gives us the sense of depth. Okay, that's not a fake sense. That's the true depth. And the thing is that for the close by objects, this depth feeling is much more stronger. Okay, because I mean, if I look at my thumb with my left eye and my right eye, it looks so different. I mean, compared to the background. Do this experiment yourself too. Look at your thumb. Okay, close one of your eyes and switch the other eye. As you see from left eye to right eye, your thumb moves a lot. If you do the same experiment for far away objects like the slide, like the corner of the slide, left eye and right eye, the slide corner doesn't change much. Okay, that's because the disparity is so low. Okay, so this is called parallax. Okay, points at different depths displays differently, and we use this a lot to estimate the depth. The same thing happens during the motion too. I mean, if I am traveling on a highway very, very fast, well, in that case, I am kind of using this parallax too. Nearby objects, okay, they seem to move very, very fast, but far away objects, they don't seem to move much. They stay the same if you look through the window of your moving car. Okay, so you might say that what does this have anything to do with the stereo? I mean, if you take a picture of the world at time t0, and if you take the picture of the world at time t1, and my camera has moved like maybe 10 meters between t0 and t1, I am looking at the same scene from two different angles, right? It's kind of a stereo. Okay, it's not like two eyes at the same time. At two different times, but the world didn't change. I am seeing the same world for two different views, and the same thing happens here. For the nearby objects, things move very, very fast. For the faraway objects, they don't move much. And if you look at for example, moon, when you are traveling and you are looking at the moon from the side view of your car, you will see that the moon doesn't move at all, it just stays there because it is too far away. Okay? Good, we already know that. People have realized this, and starting from 19 or 1800s, 1600s, I don't know, they have invented these pictures. It is called anaglyphs. Okay? Anaglyphs are images like this. What kind of a weird image is this? Okay? Well, it's an image. There are kind of two images in it. They say that, first of all, it's a grayscale image. Okay? There is no color information. You might say that, but I am seeing red and cyan. The idea is this. The idea is this. You go to, okay. You go to one place, you take an image with a camera, okay. I actually have two cameras at the same time. You take one image, left image, okay, and you save it as an intensity image, grayscale image. In this case, I am showing this image as a red image. So the bright red means it's a bright region, dark red means it's a dark region. I'm just showing it as a red, okay? And I am taking the same scene from a different view, and this time I am viewing it as a green image, okay? So this green image is different than the red image actually. Let me do it this way. This is my green image. By the way, see, do you guys know this? This is RGB. If you combine green and blue, you get cyan color. So this is blue, this is green. If you put them together, you get this color cyan. So this is a cyan image, and this one is a red image. See, there are two images, left image and right image, and two images are different. Why do I know that? How do I know that these are different? see this barrier, okay, handrail here. It moves a lot because that handrail is very close to me, right? So the nearby objects move a lot. Far away objects, they don't move much. But if I put all these two images together, one is a cyan image and the other one is a red image, you get this image, okay? So by looking at this image, you don't see any three-dimensional information, of course. You don't see any three-dimensional information, of course. But if I show only this red part to my right eye and the cyan part to my left eye, okay, then since my left and right eyes are seeing two different images of the same scene, like my eyes are there, then I will get a 3D depth sense, okay, and we can do this by means of this kind of a glass. This glass has just two transparent glasses on it, very simple glass, you know, these 3D glasses, okay. This one filters the red colors, so this one will not see the red image, and this one will not see the cyan image. This one will see only the cyan part, this one will see only the red part, okay. So my eyes are seeing two different things when I look at this image, okay. One is seeing the left, one is seeing the red image, the other one seeing the cyan image, okay. And my brain kind of process that information like my regular left and right eye do. Then I get a sense of depth from a single image like that, okay. Of course, I am not seeing any color. Everything is in the gray scale. That's called, okay, Anaglyphs. And these were invented very long time ago. People have been watching videos, watching cinemas, or looking at pictures using this simple cardboard glass. Okay, so and I think this is an anaglyph taken, made from images from Mars. Okay, on Mars we have a rover. It has two cameras on it, left camera and right camera. Mars rover, okay, Mars rover camera, okay, it is mast, right? Yeah, I think it is this one. See, this is the camera mast for the Mars rover, left camera and the right camera. It sees from two different angles, and in fact 1, 2, 3, 4 different cameras, but we are using these two RGB. The other ones are kind of different. Okay, these two cameras, these are taken. If you take those two images and make an anaglyph out of those and show it to the user, you would get this. And if I wear a 3D glass like this, my left eye will see the red, one of my eyes will see the red image, the other one will see the cyan image, and my brain will put them together and it will see that these two large rocks are much closer to me than these rocks. Okay, that's what I am going to see. And you can see all kind of other stuff like those. And well, it's kind of a novel thing. It's kind of a novel thing. People like looking at images like those. But if you look at the images like those, okay, your eyes kind of becomes like this. It hurts. Okay, so you cannot live in a world with those kind of glasses. That doesn't feel natural. That's why these kind of technologies are only for entertainment purposes, for a few minutes, maybe at most 2 hours or 1 hour. You know those Oculus, very nice, very expensive Oculus head-mounted glasses. After 5 minutes, maybe I start getting headaches. I feel nausea, and if I insist using them more than half an hour, then for the rest of the day I get my migraines. That's not going to be good. But I mean, it's a good thing to know that our eyes work this way. But if you push your eyes too much, it's not going to be good. Okay. So that's how the anaglyphs works. Okay. So basically, one of your eyes will see this cyan image, the other one will see the red image. Do I have the image for that? Let me try to open. I think I have the same image here. Open it. Do I have? Yeah, recent. Yeah, okay. I have the same image here. Yeah. See this? I mean, if I don't use the glasses and if I look at this image, I will see this. But if I look at this image with the glasses, one of my eyes will see this image, the other eye will see this image. Okay, so that's how the anaglyphs will work. Okay, so how do you make an anaglyph then? You take a grayscale stereo pair. It has to be grayscale. Okay, copy the left image to the red channel, copy the right image to the green and blue channels using a image processing utility like this GIMP. See, I can show these channels separately, so I can put those two grayscale images as red channel, green channel, blue channel, etc. And at the end, you will have your 3D image, anaglyph image. Of course, you need to use this red, cyan glasses. Okay, so we know that using, two eyes will help us understand the depth. And I know that understanding depth or estimating the depth is not just because we have two eyes. Okay, there are other information about the depth, and people in 1960s they started talking about this. Okay, how does the stereo depth perception work? Okay, is it about high level information, or is it about the information from the smallest part of the image, from the pixels? Okay, some people say that we estimate the depth because of these kind of features. For example, vanishing points. Okay, what's a vanishing point? Vanishing point is this. I know that. Okay, I know that this line and this line, I know that. Let me try to draw it. I know that this line and this line are parallel in the real world, and they will intersect somewhere. Okay, so those are the vanishing points. So when my eye looks at the real world, I see these kind of vanishing points. Okay, and the objects near the vanishing points are, I know that they are far away from me. So vanishing points help a lot as a human being, help a lot to estimate the depth of the objects. That's one thing. The other thing is that, okay, we know that this is a person and this is another person. I don't think that this person is much smaller than this person in reality, but I see this person as a smaller one because she is away from me, right? So by looking at the object sizes of similar objects, you will get this sense. For example, the chairs here are larger than the chairs over there. Why? Because this chair is closer to me. Okay, this chair is closer to me. That's how I know their depths. So these are all about high level depth cues. Okay, another one is the occlusion. Okay, I know that this object is in front of this other object. I know it because I can see the whole object, this yellow object, so this is occluded. So this occlusion gives me lots of detail about who is closer to me. For example, I know that this umbrella is closer than the light post here. Why? Because it is occluding it. I cannot see the light post the middle part of it. Okay, so occlusion is another high level depth Q. So some people say that we see the depth because of these kind of high level Qs, because we recognize objects, because we know how the real world works. Okay, some other people say that no, that plays a factor definitely, but at a much lower level. With our two eyes, we do stereo processing, we do depth estimation. So they came up with this idea. They say that, okay, this is a random image, random pixel image, okay, just pixels are random. So what am I going to do with it? I will take this part of it and I will move it to the left, and I will put more random dots in this new space. So what did I do? In effect, I created a fake disparity between this part, okay, and the original image. The original image, these parts did not change. My new image, okay, these parts did not change. Only the center part changed. So I created two image. One is the original, the other one is the center part shifted to the left. And if I view these two images as a remember our anaglyph image, you will see something like that. If you put your glasses on, you will see that there is a large cube floating over the background. So you will feel that some part of this image is closer to you, because there is a disparity at the center parts of the image. Around here there is a disparity. At the other parts there is no disparity, it is all zero. So you will sense some kind of a depth out of this image. That means what? Without using any high level cues, without using vanishing points, or without using any occlusion and etc., I can feel depth. That means what these guys are saying, okay, or in 1960 they realized this, okay. They say that stereoscopic depth could be computed in the absence of any identified objects, in the absence of any perspective, and in the absence of any cues available to either eye alone. Okay, so they have invented this. I know that my left and right eye are doing some kind of a disparity extraction, disparity search. Okay, of course we use the higher level information to estimate more depth, but at the lower level we are doing this too. So that kind of motivated us to do stereo that way. And this is how you do your own anaglyph object. You just random dots, then take the center part, move it to the left or right, and show it to the user as an anaglyph. Other people have found better ways of doing this. They call stereograms. The problem with anaglyph is they cannot be in color, right? Because I am using left and right image as our R channel and the G channel, etc. With the stereograms, everything is in color. Well, you don't encode exactly the color information, but you guys know these kind of images. Did you see these kind of images? You see it, right? It just kind of works for some people, it doesn't work for some people. But if you, I don't think that it's going to happen with a projector and you are far away. You need to be close. I think you need to look at this maybe from half a meter away. When I look at this image, can anybody see what's contained in there in 3 dimensions? I think I looked at this one today and I was able to see it, but I can't do it now. I have to concentrate, but difficult to concentrate by talking. Okay, I think there is this planet Saturn. I think planet Saturn on this one. Okay, so one sphere is floating around. Of course not. Of course it is not dynamic. Okay, so you feel that sense out of it. So it is done by small shifts of repeated texture to encode the disparity. Okay, for this one you don't need the glasses. It's just physical, the eye illusion, optical illusion, but you see a 3-dimensional shape out of that one, and that's called stereograms. Okay, so let's move on. Let's do some mathematics, let's do some geometry about this stereo system. Of course, we are going to look at this simple system. Okay, let's say I am looking at the real world from 2 different angles, and my cameras are kind of parallel to each other. It's not like human eye, even though it looks similar to this one, we don't look at the real world in a parallel way. I mean, we cross our eyes, right? When I look at the nearby objects, I cross my eyes. When I look at the faraway objects, my eyes kind of becomes parallel. Okay, so we keep changing our eye directions all the time. That's how we work. Okay, in this case, we assume that we have 2 cameras. They are looking at the same 3D world from 2 different points, but their z-axes are parallel to each other. Okay, if there is a real world object P here, okay, this one, if I project it, it will be projected here, and if I project it here, it will be projected here. Okay, so this is PR and this is PL. Okay, so as you see, let me put, okay, as you see, PR is closer to PL is closer to the left right edge of the image. PR is not that close. Okay, that's how the things work. Okay, so I am trying to guess the depth of this point P from this stereo setup, and I know that these 2 cameras are exactly the same thing. The only difference is this right camera is shifted by this amount on the x-axis. My x-axis is shifted by tx. Okay, so my left camera is at 0, 0, 0. My right camera is at tx 0, 0. Okay, that's the only difference, and this will make our job a lot easier to calculate the depth of this position P. So as always, we like to switch to, instead of working on 3-dimensional world, let's work on the 2-dimensional world, and our cameras will be 1-dimensional cameras. The picture will be like this, right? Okay, if my camera is a 1-dimensional camera, and if the world is a 2-dimensional world, this is what's going to happen. Okay, so there is a tx difference. This is 0, 0, 0. This is tx 0, 0. And this is my p point xyz. Okay, I know this xl, I know this xr. They correspond to each other, I know that. Okay, and I am trying to estimate this z, but it shouldn't be that difficult, right? Why? Because there is a relationship between, there are two triangles. The first triangle is this one. This is my first triangle. You see it. And this is my second triangle. Maybe a better color. This is my second triangle. Okay? So I know that this distance, okay, and this distance, and then this distance, and this distance, they are all proportional to each other. That's the similarity of the triangles. Using the similarity of the triangles, we are going to estimate this depth z. Okay, I know tx, I know where my camera is. Okay, I don't know z, but I know xl and xr, so I can calculate this distance here. Also, I know this much. This is f, focal length. That's what we are going to. That's what we are going to do. So basically, this is the picture that I drawn before. No problems. I have battery. So if I calculate the xl and yl for the left image, I get f times x over z, f times y over z. I will not talk much about this y because, I mean, y did not change between the y positions of these 2 points are the same. Okay, their x positions change. See, this is the x position of the left image and this is the x position of the right image. Okay, and this distance here is very different than this distance. I couldn't draw it right, but let me try to do it. Okay, so this x distance on this image and x distance on this image are very, very different. By looking at those x distances, we are going to make this depth estimation. So I have written the formula for this point. Okay, we call it xl and yl or pl. I am going to write the same equation for this point. So how am I going to write it? It is exactly the same, x over y or x over z times f, but the thing is that this camera is shifted to the right by tx. So how would you approach this problem? What would you do? If this camera is shifted by tx, that means that all of my points in the real world, okay, are doing the same thing by tx. So if I subtract this tx from all of my x values, then I can write the same thing for the right image. So this is what I'm going to do. For the xr, take the attendance. xr, maybe I can say f times x minus tx over z, right? For the yr, it will be exactly the same thing because my y's are the same. They don't change. Okay? They don't change. So I have a formula for xl and I have a formula for xr. Okay? Tell me what is xl minus xr is. xl minus xr is what? Disparity, right? It's the difference between these 2 points. Disparity. It is something that I am looking for. Let's write it then. So if xl minus xr is disparity, okay, then disparity is equal to f times, what is xl? X over z minus f times x minus tx over z. So let's do this. Okay, let's do these calculations. How do I, okay, let me make it smaller so that I can fit it in here. Where did it go? Okay, make it smaller, not shift to the right. Okay, good. So it is d is equal to f over z parentheses x minus x minus tx, right? Is that correct? So d is equal to f times tx over z. Interesting. So what do I know? Given this setup, what do I know about this setup? Assume that I know this x, tx, I know this tx, okay, I know how much I shifted my camera from left camera to the right camera. I know the difference between these two eyes, right? Usually for the human eyes, the difference between left eye and the right eye are around 5 centimeters or 6 centimeters, okay? I know that much, okay? I know the focal length of my cameras from the camera calibration. So if I know tx, if I know f, I can measure d from this correspondence. If I say that on my left image, let me go to the, okay. If I say that on my left image, this is x position 50 and this is x position 30, so the disparity is going to be 20, okay. So I calculated my disparity. If I can do this correspondence, if I can say that these 2 points correspond to each other, I know that, okay, those points correspond to each other. So if I know this d, I know these two from the camera calibration, then I know z, right? What is z then in this case? Z is equal to, okay, f times tx over d. Okay, so let's look at this one. Let's look at this equation a little bit. If d is large, okay, if disparity is large, z is what? Small. The objects are close to me. If d is small, then z is large. If d is kind of 0, it means what? My z is at infinity, right? That's good. Okay. So by formulas we figured out that disparity and depth are inversely proportional to each other. Okay. And the focal length is involved. Tx is involved in this picture. Okay, let's look at this tx a little bit. What is the effect of tx? If tx is very, very small, let's say if tx is 0, what does that mean? I am taking the same image of the real world. In that case, whatever d values, my d values will be 0 too, right? I mean, if I show you the same image 2 times, correspondence will give me exactly the same thing. So my disparities will be 0, my tx will be 0, it will be 0 over 0, and that's going to be like undefined. I mean, this doesn't work. So if I try to use the same camera for the stereo, this will not work. You shouldn't use the same camera. So your camera should be different in position. But how about this? Remember our stitching examples? Okay. If this is my camera, it is My camera is looking at this point P. Okay? And if I do this, this is where I get my point. If I rotate my camera, and my camera becomes like this, I have rotated my camera, and I am taking the same image, and on my new camera, I get this point P here. Okay? So, see on my image, blue image, and my red image, my blue image is going to be like this, point P will be here, and my green image is going to be like this, point P will be here, right? So the disparities are different. Maybe I should do this. Yeah, this is much better. So this will be the disparity, right? This will be the disparity. So disparity is non-zero. So if I put disparity in here, in this formula, D is non-zero, but Tx is 0. Why? Because I didn't change the central projection of my cameras. Okay? I just rotated my camera. Okay? If you rotate your camera and without moving it, if your central projection is the same, then stereo will not work. Okay? For stereo to work, you need disparity and a difference between the camera central projections. This value is called baseline length. Okay? This baseline length cannot be 0 for stereo to work. Okay? If you keep your camera the same, it will not work. Maybe I should give you a biological example. What did I say about the faraway objects? If I close my left eye and right eye, I see exactly the same thing at the faraway objects, right? It doesn't give me any advantage about the faraway objects. But to get more depth information about faraway objects, sometimes I do this. If you do this, I definitely know that the frame of the window is much closer to me than the funny houses over there, right? Whatever those houses are. I don't know, okay? If you do this and this, so it's kind of, I am making a larger baseline, okay? When you do this, I am making my baseline much larger, okay? This works, but if I do this, this will not work. By rotating your head left, right, okay? Or by doing this by looking left, right, with your eyes, by rolling your eyes, you will not get any depth information out of this world. Okay? To get more depth information, you have to do, sometimes we do this, right? Left and right, making a larger baseline. So if you make your baseline large, okay, that will cause more depth, more disparity for you, okay? And your baseline will be away from the 0, and that will give you a better Z calculation, depth calculation. Okay? So, we are developing a geometric model for the observations of our stereo system, our human stereo system. It kind of works, so we verify that whatever I am giving you works in the real world. That's how the engineering works, that's how the science works, right? You make some observations from the real world, and you try to model the same thing using equation, using mathematics, okay? Once you get your results back and you verify that your observations are consistent with your mathematical model, with your geometric model, it looks like it is consistent, at least to some degree, and we can continue then. No problem, okay? I think I did the same thing. So this guy says that for the camera on the right, all the points are kind of x minus tx. Right? What are those guys doing? I mean, yeah. Let me close that door. They are making noise. How much time do I have? 5 more. You have more time. Okay, so this guy is saying the same thing. Okay, for this camera, everything is kind of shifted to the right, so I am going to extract the value tx from all the x values, and put them together, do the same derivation and exactly the same thing. Z is equal to f times tx over d. Okay, so this equation says that if you have if you know your f and tx, if your cameras are calibrated, then get me the disparity. I will give you z. Okay, I will give you z. But what happens is, what happens if I know the depth of an object? If I know the f and tx, then can you get d? Of course you can get d, but that's not something useful. I mean, nobody in this world, other than the people who took this computer vision class, nobody would know about the meaning of the disparity. Everybody knows the meaning of z, depth. But I mean, finding disparity, you get your disparity from the images, not from the formula. Okay, so we already concluded this. Depth and stereo disparity are inversely proportional. We already said that. And back to this image. Okay, back to this image, and we kind of verified it. Disparities for the nearby objects are larger than the disparities for the far away objects. Okay, so let's go back to our definition of the multiple views. Okay, we said that single image does not directly produce depth. Okay, single image does not directly produce depth. Multiple images can produce depth by triangulation. We said that, and many living things use this for their advantage, but only these kind of living things does that. Okay, so this is like the stereo vision system of humans. Okay, eagles, lions, wolves, the living things that eat other living things. Okay, living things that eat animals to survive. Their eyes are kind of like that. Okay, their eyes are in front of their head, and there is an overlap of their field of view. Okay, so the human eyes are like that. Okay, the tiger's eye like that. Eagles or the owl's eyes are like that. Okay, for the other animals like the ducks, many birds, right, cows. I mean the animals that are eaten, their eyes are like that. They don't use stereo that way. Okay, their left eye and right eye, they see completely two different things. Since their field of view do not overlap, they don't get the sense from their stereo, right? Okay, they don't get the depth from stereo. I think horses are like that too, because their main thing is that, okay, stay alive. Don't let anybody eat you. Okay? Okay, if I am a horse, then I should be careful about those wolves, right? Okay, so if I am seeing the whole of my left side, and if I am seeing whole of my right side, left and right side, and then I am safe. But these kind of animals, they say that, okay, well, I can be eaten too, but the more important thing is that I have to eat somebody to stay alive. So this is kind of, well, we are kind of making this up, but that's our observation. That's our. I mean, if a living thing is eating other living things, hunting, okay, then they have a structure like those. Their noses are. It doesn't obstruct their vision. Okay, let's go back to this epipolar geometry, and we are going to make some definitions. Okay, don't get scared, and you already know that. Okay, my left image pi and my right image pi prime, left image and right image. This is my central projection of my left camera and central projection of my right camera. There is a real world point P. If I project this P on my left image, it's going to be small p, and it's going to be small p prime on the right image. Okay? So I know that all of these points, okay, will be projected to this green point here. I know this much. And the same thing, all of these red points will be projected to this red point here. I know that much too. Okay. So we will come to this again. But let's make some observation on this geometry. I see this plane. This plane is O, P, and O prime. Central projection of left, central projection of right, and P. Our real world object position P. Okay. So if I connect these 3 points, I will get a plane. Okay. This is a plane. This gray shaded plane. Okay. It connects these 3 points, and it is called the epipolar plane. Okay. It is called the epipolar plane. Epipolar plane is important because, as I said before, all these green points will be projected to this P, okay? But all of them, if I look at these green points from this camera, they will be on this line, right, on this image. It will be on this line. Okay? It will be on this line. And the same thing is valid for the other image too. Okay? It will be all on this line. Okay? So what does that mean? If I am looking for the corresponding point for P, I am going to look at it at this green line. And if I am going to look for the corresponding point for this P prime, I am going to look for it on this red line. Okay? On this red line. That's why they have special names. These two lines, L and L prime, are called conjugated epipolar lines. Okay? These two lines are called conjugated epipolar lines. Why they are conjugated? They are given special names. It's because if you are going to look for the corresponding point for this P prime, you find this conjugated epipolar line and you look for it on this line and do the same thing for P like that, vice versa. Okay? So these two lines are called conjugated epipolar lines. These 2 points are special. This point here, E, and this point, E prime. E and E prime are the points where this line that connects O to O prime intersects the left and right image planes. Okay? Draw a line segment between O and O prime. It will intersect pi and pi prime at 2 positions. One of them will be E, the other one will be E prime. Okay? Those are called epipoles. Okay? And of course, this line segment here that connects these 2 points O and O prime is called baseline. It is baseline. So I made 1, 2, 3, 4 definitions. It is all about this plane here. And this whole thing is called epipolar geometry. Okay? Once we know, of course, knowing these definitions are okay. You may get confused about their names and you may not remember their names at the beginning, but we will talk about them a lot, so you will remember them hopefully at the end of this lecture, or maybe the after midterms lecture. we will talk about them a lot, and we will write very nice formulas for these using these relationships. The important thing is that, okay, again, I keep talking about this search over and over and over and again, and that searching, I mean, instead of searching, I have a point P. There is a corresponding point on the other image. Don't look at the whole image, only look at this line. Find that line, and on that line look for your corresponding point. That's the geometry, okay? That's the geometry. It doesn't depend on your image. It is the geometry of the cameras. On that image, you are going to find the corresponding point, and that's image dependent. Those E and E prime are special points because, see, just imagine you move this point P here, okay? Now I have this point P2. What happened to your epipolar plane? I have now this epipolar plane, a new one, right? So it will be shaded like that. Everything has changed, right? My epipolar conjugated epipolar lines has changed and everything, but your E and E prime will not change. Why? Because all the epipolar planes has to go through that O prime, right? So this E prime has to be E prime has to be parts of all the conjugated epipolar lines. My conjugated epipolar lines will be always, okay, will be always doing this. Okay, this is another conjugated epipolar line, another one, another one, another one, another one, another one, another one. Okay, so the same thing for these. So all the epipolar lines has to go through this E and E prime. Question for you. Where is the epipolar point for these two images? Well, I mean this image, for this image, there is an epipole, okay? There is an epipole where all the conjugated epipolar lines go through, okay? Something like there is an image part. Where is the epipole for this image, and where is the epipole for the other image? Let's draw some epipolar lines, conjugated epipolar lines. I think I drawn this before, right? This is a line, epipolar line. This is the corresponding epipolar line. Okay, these are two conjugated epipolar lines. So this is another epipolar line and another epipolar line. You get the idea, right? These are all parallel. So where do they intersect? They intersect at come on, say it, don't worry. They intersect at infinity, right? For both of these images, our epipoles will be at infinity. Thanks to the homogeneous coordinate system, we would be able to tell exactly where in infinity, at infinity, those points will be, okay? So for these kind of special images where the images are rectified, our epipoles will be at infinity, okay? Not like that, and we don't prefer these kind of stereo systems actually. We prefer the systems where our epipoles are at infinity. Because if your epipoles are infinity, then your epipolar lines are parallel to each other and your images are rectified. Okay? Good. So the epipolar constraint says that for this point P, find the conjugated epipolar line on the other image and make a search on that image. That's called the epipolar constraint, and that will make our life in the stereo depth estimation a lot easier when you do the search. Okay, so any questions up to now? So let's use some of our knowledge about this epipolar system, and let's see if I can derive some compact, nice formulas out of it. But before that, let's say I have a plane like that. I have a vector on this plane, vector v and vector u. Okay? Tell me, how would this look? U cross product v, v cross product u. What kind of vector would I get out of this u and v if I cross product them? If you take the cross product of two vectors on the same plane, then what happens? You would get a vector perpendicular to these two, right? Okay, so it would be perpendicular to this plane, and it will be a new vector z. Okay. So how about this then? If I know that there is a vector, let's say k, and I know that this vector k, and I know that this vector k is perpendicular to this plane. Okay, I know this. U and v are just two vectors on this plane. K is another vector that is perpendicular to this plane. Then I know that v dot k, this is an inner product, dot product, and u dot k would be what? This is a vector, right? U cross product v is a vector. V cross product u is a vector. But v dot product k is not a vector, right? It's just a scalar. But what kind of scalar is this? It is what? It is zero. Okay? If two vectors are perpendicular to each other, their dot products will be zero, right? I know this much. But how about this? V cross product u dot v. You would get what? Zero, exactly. Okay? You would get zero, because I am just multiplying this, which is a perpendicular to both u and v, with v, then I'm going to get a zero. So that's what I am going to do. I am going to take this three vectors, this vector, okay, O prime vector, that's one vector. The second vector will be OP vector, okay, OP vector, and the third one will be O prime P vector, okay. So these three vectors are on the same plane. If I cross product these two, and if I do a dot product after that with O prime P, I should get a zero, right? O prime times cross product OP will give me a vector perpendicular to this plane, and if I dot product that vector with O prime P, I would get a zero. Okay? I would get a zero. I will use this to write the equation about this epipolar geometry, and that equation is going to give me lots of useful stuff. But most importantly, maybe it will give me formula for this line. Given this point P, that equation will give me formula for this L prime, or if you give me this P prime, that formula is going to give me this L, okay, this L. That's what I'm going to do. So let's get this one. Remember those three vectors, OP, O prime, P prime. By the way, OP and OP are the same thing, right? O prime P and O prime P prime are the same thing, okay? So this guy says that OP, O prime, P prime, O prime are on the same plane, they are coplanars. And if I write this, O prime cross product O prime P prime, and the resulting vector is dot product by OP, should give me a 0. Okay, and I'm going to work on this. But before that, let's remember some algebra. You know this, right? That's the definition of the cross product. That's the definition of the cross product. How do I produce a cross product of two vectors? You write A1, A2, A3 here, B1, B2, B3 here, okay? And you do this, okay? Take the determinant of this one, determinant of this one, and determinant of this one. A2, B3, okay, minus B2, A3. Then this and then that. That's the definition of the cross product, okay? But given this definition, how about this? What is this? A. If I take a cross product of a vector by itself, what happens? Well, let's calculate it. A2, A3, A2, A3. That's going to give me what? 0. And this one is going to 0. This one is going to be 0. So this A cross product A, by definition, gives me a 0 vector, right? So that's the definition of it. That's the definition. Well, you already know that, but maybe you didn't know this. This notation is nice, but in linear algebra, we like to multiply things by matrices. So somebody has invented this. They say that if this is the definition of the cross product, maybe I can pose it, maybe I can represent it, maybe I can formulate it as a matrix product. Okay, you would do this. Okay, you would do this. Write a matrix like that. Okay, this is called a skew symmetric matrix representation of A. Multiply this matrix with B vector, you would get the cross product of A and B. So this is what would be the, okay, 0 times B1 minus A3 times B2, A2 times B3, that will be your first component. So it will be B1, okay, how it's going to be, okay, A2 B3, right, these two multiply, so A2 B3 minus A3 B2, see, I get the first component. And do the second line and the third line. See that we have this skew symmetric matrix, okay. It is symmetric around here, but it is not perfectly symmetric. Why? Because A3, A3, A2, A2, A1, A1, but minus, minus, minus here. That's called skew symmetric matrix. If I multiply the skew symmetric matrix of A with B, you would get the cross product of A and B. So I am doing exactly the same thing, but I am using my matrix multiplication, matrix and vector multiplication method, which I like a lot because that kind of makes everything linearized. Okay, we like to be in the linear world. That's what I am going to do. Okay, I will represent this OO prime as a matrix. So this product will be a matrix multiplication, Okay. After the matrix multiplication, there is another vector, and that will be my final thing. But it looks like I need to let the people come in, and I need to stop at this point. So that means what? Next week we will have our midterm exam, right? So midterm exam is up to this point. Okay, this slide is included, and it will start at 14:30, and it will be a 120-minute exam. Okay, everything is included. Good. Any questions so far? Okay, now I will see you next week then.